In this lesson, we're going to learn about molecular compound. The smallest building block of a molecular substance is a molecule. A molecule is made up of multiple atoms. A molecular element consists of molecules that contain atoms of only one type of element. An example of molecular elements include ozone, which is O3, and sulfur gas, which is S8. Some molecular elements are made up of two atoms bonded together, and they are called diatomic molecules. Common examples of diatomic molecules include nitrogen gas, which is N2, and bromine, which is Br2. In question read, what properties do these molecular compounds shown in this table here have in common? And what distinguishes molecular compounds from ionic compounds? So think about it and answer in the comment section below. What do molecular compounds have in common? First, they have low melting and boiling points, and that is because they have weak intermolecular forces. Don't worry about it, I'm going to make a separate lesson on this in the future. Furthermore, they have poor electrical conductivity, and you will see why later in this course. Also, they are soft and brittle. Last but not least, they have lower density compared to ionic or metallic compounds. The force that holds molecular compounds together is the covalent bond. So let's learn about it. Based on the location of hydrogen in the periodic table, we can see that each unbounded hydrogen atom has one unpaired electron in its valence shell. And this unpaired electron is called a bonding electron, and it is available to form a covalent bond with another atom. The number of bonding electrons in an atom can affect the number of bonds it can form, and this number is known as the bonding capacity. From this table here, notice that hydrogen is stable with only 2 valence electrons, not 8, like most other elements. In this example here, when two hydrogen atoms collide, the proton of each atom attracts the electron of the other atom. And that is because oppositely charged particles can attract each other. As a result, the two atoms share their electrons and form a hydrogen molecule, H2. And the attractive force or bond that results from the sharing of an electron pair is called a covalent bond. And now we can conclude that covalent bonding requires share of electrons. When we use Lewis symbols to represent the bonds within a molecule, we produce a Lewis structure. Lewis himself used only dots to represent all the electrons. Chemists now typically use a single dash to replace each pair of bonding electrons. When two oxygen atoms combine to form molecular oxygen, O2, the oxygen atoms share two pairs of valence electrons to satisfy the octet rule. When atoms share two pairs of electrons, they form a double covalent bond. Similarly, when two nitrogen atoms combine to form molecular nitrogen, N2, the nitrogen atoms share 3 pairs of valence electrons in order to satisfy the octet rule. And when atoms share 3 pairs of electrons, they form a triple covalent bond. The lone pair refers to the electrons that are not involved in bonding. In this example, the lone pairs would be these electrons. So far, we had a look at some diatomic molecules. Now, let's examine some cases where more than one molecular element is involved. This image here shows a molecule of hydrochloric acid, and we're going to talk about acids later in this course. Hydrochloric acid forms from one atom of hydrogen and an atom of chlorine. Note that they share a pair of electrons, forming a single covalent bond. In this way, both atoms fulfill the octet rule. Therefore, hydrogen chloride, or hydrochloric acid, is formed. Chemists often simplify their diagrams even further by only including the covalent bonds in their diagram, and this representation is called a structural formula. We have looked at some simple molecular compounds like water and oxygen gas. However, compounds such as sugar and lactic acid, like the acid found in your milk, They're made of much larger and more complex molecules. And one feature they all have in common is that they contain a lot of carbon atoms. And representing them by Lewis structures or even structure formulas will be time-consuming and cluttered. And therefore, biochemists have developed another style of diagram called skeletal formula or skeletal structure. Basically, they leave out all the carbon and hydrogen atoms and just show their bonds. And because of the bonding pattern of carbon, the bonds almost always change direction at a carbon atom. And here's a visualization. And you can therefore assume that there's a carbon atom at each angle or intersection of the bonds. However, we won't go further in this topic. You have seen a few Lewis structures and structure formulas. You have to learn how to draw these diagrams. But when it comes to drawing a molecule of CH2O, or methanol, it involves around 10 steps. So step number 1, arrange the symbols of the elements in the compound so that element with the largest bonding capacity is in the center, surrounded by the elements with smaller bonding capacities. So here's a table of reference. As you can tell, carbon has the largest bonding capacity of 4, while hydrogen only has 1 and oxygen has 2. And step number 2, count the valence electrons for all the atoms in the molecule and record the total number. And step number 3, place 2 electrons between the center atom of each of the surrounding atoms. So we've got a diagram like this. Step number 4, place lone pairs of electrons around each of the surrounding atoms to satisfy the octet rule. Remember that we don't have to draw lone pairs for hydrogen because hydrogen does not follow the octet rule. Then we get to determine the number of electrons that are still available. In this case, non-valence electrons are remaining, so we don't have to do anything to carbon. If not, we have to place the remaining electrons to the center atoms in pairs. And if the center atom does not have a full octet, we have to move lone pairs from the surrounding atoms into a bounding position between the central and surrounding atoms. So in this case, we have to move this lone pairs to here. Now the center atom has a full octet. We have to replace the shared pair of electrons with dashes to represent the covalent bond. And we can use double or triple dashes for double or triple bonds. And lastly, to convert the Lewis structure to a structure formula, just simply remove the dots representing the lone pairs. And now we've got a structure formula for methanol. And here's another sample problem that teaches you how to draw a Lewis structure for a polyatomic ion. And I'll give you 5 seconds for each slide, and you guys should figure them out by yourself. If you have any questions, feel free to ask me down in the comment section below. And here are some questions for you to practice. In the end, I have to pull up the table for you. It basically compares the physical properties between ionic and molecular compound, and you guys can read it through. And here's a summary for this section. And that's about it. Thank you for watching, and I'll see you in the next episode.